Hello! Today I'm going to talk a little bit about the force of gravity. Now, we all experience gravity every single day, and most of us know the basics. It's what keeps us tethered to the ground, and it's what makes a ball fall back down after it's been thrown up in the air. But in order to truly understand how gravity works, and to understand how Earth's gravity compares to the gravity in other places in the universe, we need to first understand what factors influence gravity. And one way we can do that is by analyzing the equation for gravity, which is F sub g equals g times m1 times m2 all over r squared.
In this equation, big G, as it's called, is the universal gravitational constant, shown here. This constant is the same for gravitational forces all across the universe, and it's given in terms of meters cubed per kilogram seconds squared. Next, we have m1 and m2, which are the masses, in kilograms, of the two bodies that the gravitational force is acting between. And finally, we have r, which is the distance, measured in meters, between those two bodies. So what this means is that if we had two bodies that, at a set distance, had a gravitational force acting between them of 4,000 newtons, then doubling the distance between the bodies would change that force to 1,000 newtons. And that's because in this equation, the distance is in the denominator and it's squared. So changing the distance by a factor of 2 actually impacts the gravity by a factor of 4, and it impacts it by making it smaller. On the other hand, however, if we keep the distance between the two bodies the same, and just increase the mass of one of the bodies by a factor of 2, then the 4,000 Newton force will turn into an 8,000 Newton force. And that's because with this equation, the force of gravity is directly proportional to the masses of the objects.
So the equation we've just looked at gives us the attractive force of gravity between two bodies in terms of newtons. But another way we interpret gravity is as an acceleration in terms of meters per second squared. On Earth's surface, that acceleration is 9.81 meters per second squared. And we calculate this value using this equation, which is a slight variation on the equation we just looked at.
This equation is used to find the acceleration due to gravity on a planet's surface. And it's derived by setting the equation for the force due to gravity equal to mg. Doing this allows us to cancel out one of the masses and leaves us with g equals big G m over r squared. And in this case, m is going to be the mass of the planet that you're looking at in kilograms, and r is going to be the radius of that planet in meters. So, to illustrate how this equation works, we can calculate the acceleration due to gravity on the moon's surface and compare it to that of the Earth. The moon's got a mass of 7.35 times 10 to the 22nd kilograms, and it's got a radius of 1.74 times 10 to the 6th meters. Plugging these values into the equation gives us the acceleration due to gravity on the moon's surface, which is 1.62 meters per second squared. By comparing the gravitational acceleration on the moon to the gravitational acceleration on the Earth mentioned previously, we see that it's much smaller on the moon because it's got a smaller radius and a smaller mass.
So there you have it, a brief look at the basics of gravity and all of the factors that influence it. Thanks for watching.